All right, hello everyone. Welcome to the 3D printing virtual tour from the HA headquarters here in Palo Alto, California. Very good morning to everyone, or good afternoon, wherever you are. Let me go over the agenda that we have for today. This webinar is gonna take an hour and 15 minutes, and we're gonna start by introducing you to multi-jet fusion technology. And then we will go over the hardware portfolio that we have, and we will show you how the 3D printing workflow. I'll go into the labs and show you a hands-on demo of how those printers works. Then after that, we will move into the materials portfolio, show you the different materials that we currently offer with our printers. And then we will do also application showcase for you guys to see customer applications. Then after that, we're gonna go into a customer panel. So stay with us for the whole hour and 50 minutes. We have a special guest here that will share with us his experience using multi-jet fusion. Last but not least, we'll devote the last 5 minutes to Q&As, but if you guys have any questions along the way, please just, there's a chat box right here in the webinar where you can just type your questions and the speakers will take them on the fly. All right, so who are the speakers for today? One is myself. I did not introduce myself, but my name is Carolina Rubio, and I work as a 3D printing customer program manager here in Palo Alto, California, in the HP headquarters. And then we also have Wes Kramer. Wes is a 3D application engineer, and he's based in San Diego. Good morning, Wes.
Morning, Carolina. Hello, everyone. Very much looking forward to this session today.
Thank you, Wes. All right, and we're also going to have a customer panelist, and it's Kaysen. Kaysen is the owner and lead engineer at Solids, and he will be with us today to tell us more about his experience using the technology, talking about his applications, and just covering a range of different questions. Also, if you guys have questions for him, we will definitely field those questions. All right, so let's start. And the first topic is, what is multi-jet fusion technology? So what you see right here on the screen is what we call the HP voxel. An HP voxel is a 3D representation of a pixel, and this is the basis of our designs and objects. So you can think that we apply agents, and later you will find out what an agent is at this voxel level that give us voxel control. So if we mentioned during the webinar voxel control, is because we're able to apply these agents at this voxel level, and then getting the accuracy that we need. All right, so let's go over the step-by-step process. I was mentioning there's agents. What exactly are agents? Well, let's do an analogy with a traditional printer where we have paper and then we have ink. In the case of a 3D printer, the paper would be plastic powder and the ink would be those agents. Now, as for the agents, we have two. There's a fusing agent that is black, as you can see here on the screen, and then there's a detailing agent. The detailing agent is transparent. To put it very simple, fusing agent absorbs energy, detailing agent does not absorb any energy. So let's take a look at this infographic for you guys to see the step-by-step. So the first step would be we spread a layer of material, this powder-based material, we spread a layer. And then we selectively at the voxel level are going to be applying agents. We apply fusing agent and we apply detailing agent. But as you can see right here, we apply fusing agent where we want that area to fuse with the previous layer. And we apply detailing agent on the exterior of the part to prevent that area from melting. So third step, we do apply energy. This is a thermal control process. We apply energy with the fusing lamps. And so with this energy, the agents react to it. The fusing agent absorbs energy, the detailing agent does not. And the result is that where we apply fusing agent, that layer is fused with the previous one. Where we apply detailing agent, that area, it hasn't melted. It's actually detailing agent is going to be evaporated when we apply the energy. And then the process starts all over again until we complete all the layers and we have the part printed. Let's take a look at this video. It shows how this process happens inside of the printer. So we're gonna take a camera inside and see how that works. Thermal control process, as I was mentioning, there's a roller that's gonna spread a layer of powder in the printer roll area. And then in the opposite direction, we have a carriage, and that carriage is gonna be spitting selectively, fusing and detailing agent. And then we're gonna raise the temperature with the fusing lamps to the melting point, and then that's where the fusing agent is going to react and melt that area where we apply the fusing agent. And then on top of the printer, we have these heating lamps and thermal camera that I'll show you in a minute in the 3D labs. And that's to control the temperature and make sure that it's consistent across all the printing job. All right, perfect. So remind you guys, if you have any questions, just type it on the chat. We'll take it on the fly. Before we move into the next one, actually, the next one is the hardware portfolio, and then the end-to-end printing workflow. We're going to do a hands-on demo right now in the 3D labs. But before that, let me walk you through the portfolio that we currently have, focusing on production. So we have two solutions, the 4200 and the 5200. The 4200 is intended for functional prototyping, low mid-volume production, and then we have the 5200 that is intended for high-volume productivity. Now, as you guys can see, these are modular solutions. They're made up of 3 different elements. There's a printer. In the middle, you see a kind of a trolley. That trolley we call the build unit. And then we also have a processing station, the one that has that external tank connected to it. And so why do we design it that way? We want it to be modular because that maximizes the productivity. And you will see in a minute why. That trolley, we can have it printing, and we have another trolley that is loading the material and doing the pre-process of the printing process. So in general, this modular solution allows us to maximize different elements, the different devices that we have in the solution. Now, if you guys are looking for the kind of accuracy and repeatability that is closer to manufacturing level, you definitely will go with the 5200 solution. All right, let's take a look at the printing process, how the workflow works from the moment that you design the part till the moment that you get it, that you print it and you apply some finishing. The first step right here would be, let me see. Okay, it's a file preparation. So it's basically prepare the files, have the parts ready, create the build, and Wes is going to do a demo of that with the software that comes with our solution. And then once we have the file ready, we're going to send it to the printer, and then we start with the pre-processing. What that means, well, you see that trolley right there. That trolley is going to be loaded with the material, and we're going to mix the material because to make sure that the cost per part is the lowest possible, we're going to be using reused material from a previous job. Mix it with the fresh material. That will lower the cost of our printing. Then once that trolley is loaded with the material, then we're going to take it into the next step, that is the printing. So we will take it in the printer, and that will take a while for the parts to be printed. And I'll go over that in the lab so you guys can see how the printer looks like. And then once the printing is completed, we need to do some post-processing. But post-processing meaning we need to cool down the parts. Those parts are really hot. They just got printed. So we need to cool them down. There's a few options that we have here that I will also show you. And then we're also doing the unpacking. So once the parts are cooled down, we're going to extract them from the trolley. And the last step, it's cleaning them. So make sure that we remove any powder around the parts. We have a few options here. We have bead blasting, and we also have earth blasting. And last but not least, we have another step that is called, well, secondary process. We call it finishing, right? That is to apply any kind of processing to these parts. We can do surface finishing, chemical polishing. We can dye the parts. We can color the parts. There's plenty of options here that Wes will cover after. But yeah, pretty much this is the step from the moment that you prepare the file till the moment that you're able to extract the part, clean it, and then apply some finishing if you wish. All right, I'm gonna pass it now to Wes. We're gonna go step by step and show you guys a demo of these steps. So the first one would be the file preparation. So Wes, whenever you're ready.
Carolina. So I will go ahead and share my screen here. And we're take a look at HP's free build manager software, which is SmartStream. So just like any sort of build manager software for a 3D printer, I'm going to be using files like STL, right? That's kind of the standard in 3D printing for a file type. So loading a file into the software is as dragging and dropping. So you can see we did that there. We have a few simple things that we can do in this software to prepare this file for printing. So the first thing that we can do is we can pick an orientation for the part. What's nice about our technology is that means that everything is self-supporting. So in a lot of 3D printing technologies, if you were to print something at an angle like this, you would have to print support structures underneath because gravity kind of impeding natural build process. But think about how we're printing. There's going to be powder surrounding whole geometry during the printing process as we build layer by layer. So those support structures are not going to be necessary. It's all going to be self-supported. Other thing that's interesting is this is actually in a state of several individual parts, and we're printing it pre-assembled. So when this comes out of the printer, you'll be actually able to spin these gears, and it is a functioning assembly. So we'll pick an orientation that makes sense. Actually, from I think closer to flat is going to be best. That's going to give us the quickest print time, as you can imagine, because it's going to reduce the number of layers we have to print. And then let's duplicate this several times. Let's several. And you might be thinking, why would we want to print several? Isn't that going to increase the print time? Well, with multi-jet fusion, if you remember the video that Carolina showed earlier, we utilize what's called an area-wide printing process versus a point-based printing process like 3D printers would. What that means is in one single swipe, we take care of an entire print layer. And so that print layer time is going to take the same amount of time no matter how many parts we're printing on that layer. The analogy I like to use is imagine having to copy text by hand onto paper versus printing that paper out on a large office printer. It doesn't matter how many words are on that page, it's going to turn out pages at the same rate no matter what. So it's the same thing going on here. It's just printing on paper. We are going to be printing on powder. So let's print several of these since it's going to take the same amount of time, no matter, as long as we don't change the height, it's going to take the same amount of time. And we have this nifty auto pack feature, which is going to nest these 5 millimeters apart. That's what I am specifying here. So you can see we have our parts ready here in the build. Let's maybe move them towards the center. And we are ready to print. Another thing to note, it's like we showed we can print at different angles because everything is self-supporting. We can actually take this layer and we can duplicate it and stack these parts, and we could fit, definitely 100 of these parts in a single build because everything's going to be supported by the powder. So because we're area wide, because we can stack these support structures, we are definitely geared towards higher volume production in the grand scheme of 3D printing. And there's a lot of interesting things that the technology enables us to do. So that is that for file preparation. We pick our material, our print mode, and we send to the printer. And now Carolina is going to walk us through what happens after that is finished.
Okay, Wes, do you hear me okay?
Yeah, we hear you great.
Okay, I don't know if you hear me when I was saying good morning to all the people here in the labs. Did you hear that?
No.
You did not. Okay, perfect. Well, because we're in the labs and we have engineers working here, I was walking by and was like, good morning, everyone. So we're here in the 3D labs right now in Palo Alto. This is a production facility. And so right here we have a 5200, and then in the back we have another 5200. This one works with PA12, and the one that we have in the back works with PA11. So what we're gonna do right now is just walk you through the steps, the central steps that we saw in the workflow before. Just wanna make sure, Wes, can you confirm you hear me okay?
Yeah, we hear you great.
Yeah, okay, perfect. All right, so let's just show you guys how to do the file preparation, and we send that to the printer. I was mentioning earlier that this is a modular solution, and it's made up of different elements. So we have here a device, this is the printer. We have this trolley that we call the bill unit, and then this one over here is what we call the processing station. And then we also have these accessories right here that I'll show you later what this is for. Now, the first step we're gonna do is part of the pre-process is to load this trolley with the material. So I'm gonna show you guys how to do that. And I'm wearing heels today, so this is even gonna be harder for me to do, but no problem. All right, so we're gonna open here, slide in the bill unit, and then the processing station is gonna detect that and start recognizing that bill unit, checking whether is it empty or not. Okay, let me show you. I'm gonna put this up, and you guys are gonna come closer with me right here. And so the processing station right now is reading the bill unit. What's that mean is like, it's detecting whether the bill unit is empty or not. This one is empty. So what it's gonna ask is, what do you wanna do? Do you wanna do the material loading? And it's gonna ask for two things. First, what is the reusability ratio that we're gonna be using? I mentioned before that to lower the cost per part, we're gonna do a material mixing using reused material from a previous job and also using fresh material. So I want to show you guys where we have the fresh and the reused material right here. If we look with the camera right here, here behind is where we keep the reused material. And over there is where we have our fresh material. So you see right there, this supply, this is a 300 liters, 130 kilograms of PA12. And you see these hoses are connected to the processing station and they are connected up here. This is what we call the mixer. And we're gonna be mixing fresh material coming from that supply and also reused material coming from the reuse station right here. So we mix it here, and then what do we do? Well, we're gonna tell the processing station the reusability ratio that we're gonna use. For P12 in this case, we're gonna be using 80% of reused material, 20% of fresh. All right, so we will be selecting this here. The next question that the processing station is gonna ask is how tall your job is going to be. Why? Because you don't need to do full jobs all the time. You can decide how much of the space that you have, the volume of the bill unit, you're going to be using for that. All right, so once we have decided on the reusability ratio and how tall your job is, we're going to put this nozzle into the bill unit right here. And then we're just going to click load. So how long does it take to load bill unit? If we're doing a full job, that might take between 40 to 60 minutes. If you're doing half a job, that will take approximately half the time. So between 20, 35 minutes. Why am I giving these ranges? Because we have different materials and different materials load at a different speed. I'm gonna stop right here before we move into the next step, that is the printing process, to make sure that we cover questions if there's any. Wes, do we have any questions right now?
Yeah, we have pretty relevant questions actually right now. One is, are there limits in terms of powder recycling? And I would be happy to answer that one. So Carolina mentioned a recycling rate of 20% fresh powder, 80% reused material, talking about loading the powder into this build unit. And that is going to be kind of the standard refresh ratio for our PA12 material, which is our most common material. And so that is the minimum. You have to do at least 20% fresh powder with that. We have some materials that require up to 30% fresh powder. And then we have a material, polypropylene, which actually can refresh at as low as 0% fresh powder. You know, you're going to obviously have to input more than that because you're using material at the end of the day. So usually it lands at about 10% fresh powder. But yeah, there are some, theoretically, you know, if you're refreshing at the, you should be able to using that powder generation over generation and maintain its level of integrity. And then there's one other pretty relevant question here, Carolina, and it is, what material is used? Is it resin or powder? And just to clarify, we are a powder-based system. We are looking at plastic powder right now.
Plastic powder, exactly. Yeah, plastic powder. All right, so let's move into the next step. We just loaded the bill unit and now we're gonna move into the printing process. For that, let's just take this nozzle out. We put it in parking position. And then now we're going to put back the lid here. All right, tell the processing station that we're ejecting the bill unit and we'll take it into the printer. So I want you guys to see the whole process. So let's put this here. All right, we can open the front door, extract the bill unit. And then we're gonna take it into the printer right here. And so right now this build unit is full of powder. And we are going to take it to the printer. Give me a sec. Oops. All right. Perfect. And so I want you guys to see closer because there's a few elements right here that I want to show you. So if you come closer with me, let's see. All right. So for the printing process, we were mentioning earlier about, we were saying the printable area, there's the heating lamps are here, we have a carriage. So the first one that I want to show you is the top part, this one right here. So we have 20 heating lamps and we also have a thermal camera right here. And what is this used for? This thermal camera is going to be taking pictures of the printable area. And then with these heating lamps, we make sure that the temperature in the printable area is consistent. If there's any deviation in the temperature with the thermal camera, we can detect that. And then the heating lamps will adjust the irradiation of the lamps to make sure that the temperature is always consistent, layer by layer. All right. What other elements do we have here that I want to show you? The carriage. This is the carriage that it's going to be spitting fusing and detailing agent. And I'm going to open it for you. Let me see. So here, if I open it, you guys will see there's 3 printheads right here. And these printheads look exactly like this. I want to show you. Let's see if we can adjust the camera a little bit. This is a printhead. And this printhead both spits. These are the nozzles, and they spit selectively detailing and fusing agent. This is a technology that we leverage from large format printing, but we have a lot of expertise. So we have been able to use this in our 3D printing technology. Now, if I open it here, you guys will see there's, as I was saying, 3 printheads inside, both a speed. You see there's a D and an F, D for detailing, F for fusing agent. And then to the sides, there's 2 models of fusing lamps. So this is one model of fusing lamps, and this is another model of fusing lamps. And Wes, I know that you want to point out something here that's really cool.
I always love to pause here and point out the fact that these cooling channels on top of these fusing lamps are actually printed with multi-jet fusion. And so what you're seeing here is a rather complicated design that would be very difficult to manufacture with traditional manufacturing technology. And, and the production volumes are such that it definitely makes more sense in this case to 3D print. So we're going to talk a little bit later in the application showcase about some of these concepts, but this is a really interesting use case for MJF on our own technology.
Great. All right. So we have these 2 fusing models, and I want to walk you through the process in the printable area. If you come back here to the middle, just to remind you how the process works. The build unit is inserted inside, and then with the build unit, let me adjust a little bit the camera. All right. So the build unit has a mechanism to bring the powder from the bottom up. We have a roller right here. This roller is going to be spreading a layer of powder back to front. And then what we're going to be doing on the opposite direction with the carriage, with these printheads that we have right here, we're going to be selectively spitting, fusing, and detailing agent. Remember that we speed fusing where we want that area to fuse, with speed detailing where we want that area not to fuse. And then with the 2 fusing models that we have to both sides of the carriage, we're going to be raising the temperature. Remember, there's a constant temperature right here below the melting point thanks to these heating lamps. But with the fusing lamps, what we do is we raise the temperature to the melting point, and then this energy will make a reaction with the agents, and then the fusing agents will react and fuse, whereas the detailing agent will evaporate, preventing that area from melting. And then we repeat the process again. So again, the build unit has this mechanism, bring the powder up, roller, spread a layer of powder. We move with the opposite direction with the carriage, speeding, selectively fusing and detailing agent. And then we raise the temperature to the melting point with the fusing lamps. And then we repeat the process again. So we do this layer by layer until we have the full job printed. Now, questions that we normally get here: how long does it take to print a job? To do a full job, that might take with the 5200 between 9 and 11 hours. Why am I giving a range? Because we have different print modes in the printer. So you can print with a fast print mode, that would take 9 hours, or you can print with the balanced print mode, that might take up to 11 hours. And different print modes have different results in the accuracy and the visuals of the parts, the look and feel. So yeah, I'm gonna stop right here. Wes, I don't know if there's any questions around the printing.
Yeah, so one person was asking about the print speed, and so you pretty much answer that there. You know, he was asking for maybe print time per millimeter height. You know, so this would be, I guess, a decent time to talk about our bounding box dimensions. So our print area is 380 millimeters by 284 millimeters by 380 millimeters. So it's 380 millimeters tall, 11 and a half hours, 380 millimeters. I'll let you do the math there. So that is kind of our print time per height. And then there was another question from Richard. He said, you mentioned that the detailing agent is evaporated. Can it be recovered and recycled? So I can tell you, Richard, that is not currently part of the process, but I will never say never. Definitely theoretically could be a possibility in the future. However, no, that is not something that we are currently doing.
Okay, perfect. All right. Thank you, Wes. So we have completed the printing, and so now we have to cool down the parts and extract them, do the unpacking. So I want to show you how to do that. Before we extract the build unit, I want to point out something remarkable here. The printer is not going to let you extract the build unit after 30 minutes of safety cool down has happened. And it's going to happen here inside of the printer. We want to make sure safety goes first always. So we want to make sure that this build unit is at a temperature that you can manage when you extract the build unit. So at least a safety cool down will happen here for 30 minutes, and then you're able to extract the trolley and bring it and do the cool down of the parts. So for the cooling down, there's two options. We can do natural cooling or we can do fast cooling. The fast cooling is a feature that we have on our processing station. So when you want to go faster, you want to get those parts, have those parts ready, you can definitely use the fast cooling. Cooling down the parts in a natural way might take between 24 to 36 hours, depending on the geometry of the parts and the packing density that you have inside of the build unit. Fast cooling takes pretty much the same time that it takes to print out the parts. So if it takes between 9 to 11 hours, fast cooling the parts might take, around 9 to 11 hours, more closer to the 11 hours. So we're gonna do the fast cooling first so you guys can see how that works. So we're gonna tell the printer that we're ready to extract the build unit. All right, so we're gonna check that, doing the checks, and I'm gonna push it a little bit here so you guys can see both. Disconnecting. All right, let's open this. Again, so what we're doing right now is to extract the build unit. We have already completed the safety cool down in the printer for 30 minutes. So the parts are here inside of the build unit and they're really hot. And we're going with the first option that is doing that fast cooling, making sure that we have those parts fast. So we're gonna insert the build unit. Okay, wearing heels today was not a good idea. I'm sorry, guys. All right, so we'll push it in. And then what we're doing before I go, we have to use this platform right here. So the trolley has this platform that we will use for the fast cooling. We're gonna put it on top of the trolley of the build unit. All right, perfect. And so I wanna come closer and see. So now we're gonna use this nozzle right here. We take the lid off. This is super simple. And with this nozzle that we have, which is inserted, and then tell the processing station that we're gonna run the fast cooling. What is this going to do? It's gonna be vacuuming the hot air that is circulating inside of the build unit. So yeah, basically just absorbing, vacuuming all the hot air that we have. That's how the fast cooling works. But there's an alternative to this, and it's doing natural cooling. Now I wanna point out something very important. Whereas we have this build unit right here that is doing the fast cooling or even natural cooling. Remember, we have the printer empty right now. So what happens if you want to maximize productivity, we have two build units right there. So these two build units can be used. One can be left doing natural cooling, and the other one we can insert in the printer. And then, at the same time, we can do continuous printing. So you can have this system working at the same time doing different tasks. We can do the fast cooling here, we can print another job, and we can use another device to do the natural cooling of the parts. All right, so I was saying there's an alternative to the fast cooling, it's natural cooling. And in the 5200, because this is a high productivity solution, we come up with accessories that facilitate that. So these are the accessories that we have right here. This is what we call the natural cooling unit, and this is the forklift. So why this is used for? This natural cooling unit with the forklift, we're gonna put it on top of the bill unit that we have right here. I'm gonna take this off. All right, so this natural cooling unit will go on top of this, and then we're gonna tell the 5200 that we're ready to take out the job and transfer the job to the natural cooling unit. Why do we do this? Because it's easier for us to do the natural cooling in this unit than using the bill unit for that. When we transfer the job, we have this bill unit ready to do another load of material or to be printing in the printer. So in this way, we maximize all the elements of the device, the solution. All right, questions here around the fast cooling, the natural cooling. Just to mention that, yeah, these units can be left to cool down, and then when they're ready, when they 24, 36 hours have passed, then we can do the unpacking of the parts in the processing station. But before I move to the unpacking, is there any questions, Wes?
No questions about the cooling. You did a great job explaining. Ooh, actually, we just got one from Mark. He said, what are the trade-offs with fast versus normal cooling? I am happy to answer that one. So really, this is going to be something that's geometry dependent. If you have really long, thin parts, we are using thermoplastics here. With any type of printing technology, they're going to be susceptible to warpage during the cooling process. So when you do a fast cool, you are going to be definitely introducing a higher thermal gradient across parts, and it's going to increase the susceptibility to things like warp. However, if you have a pretty chunky, more robust design, fast cooling is most times going to be a pretty good option to quickly cool parts, and you're not going to have really any effect on your part quality.
Mm-hmm. Perfect. All right. Okay, if there's no more questions, let me walk you through.
There's one more, Carolina, sorry. And this was one that was asked earlier about the printing process, again by Mark. And he asked, do you have any data on the amount of residual agents remaining in a printed part? Again, I'll take that. So not that I'm aware of in terms of something that's published. However, I can say that, it is very small amounts. It is not going to affect things like the mechanical performance of the material. It's going to have very little influence overall. And yeah, I'll leave that one out there. And yeah, let's move forward, Carolina.
Okay, perfect. So we have already completed the cooling down of the parts. Now we're ready to do the unpacking. The unpacking always going to happen in the processing station. And for that, we're going to cue a video of a job that we just unpacked for you guys to see how it works. The processing station actually takes you through the process. So it gives you the step-by-step instructions on how to do it. So first it's going to complete the different checks to make sure that it's ready to do the unpacking. It's going to remind you to use globes to have everything ready, to how the system works. But with the same hose that we use for the fast cooling, what we're doing is reclaiming the powder. That powder is going to be used for the next job. Remember that for the jobs we use reused material. It's coming from this unpacking. So we start with the corners and the edges where the powder is easier to just reclaim. And then as we found parts, we just reclaim the powder that is loose. You don't need to clean the parts completely. That's going to happen in the next step with the bead blaster. Here, we're just reclaiming the powder that it's easy that is loose, right? And so as we clean the parts, we're going to put them here to the side. We have some ventilators right there. There's going to, if there's any powder in the air, there's going to be absorbing, vacuuming that powder. And yeah, basically it's just like do that process that for a full job took me like 20 minutes to do. And then once the parts are extracted, then we're going to take them into the bead blaster to clean them. So that very same part that is just extracted, that is a orthotic part, we have here one of our engineers cleaning it. But Wes, I know that there's ways of doing this in an automatic way. Do you want to talk about this?
Absolutely. So there are definitely automatic bead blasters out there, and they usually function by having a stationary nozzle, and then they have a barrel that rotates, a drum that rotates, and it circulates the parts around that stationary nozzle. So that's usually better for smaller, more uniform size parts. But for big parts like this socket, it's probably going to be better to do a manual blasting process.
Yeah. And there's also an unpacking station that we have to do that in an automatic way. Is that correct?
Yes. And so are you referring to automatic unpacking station?
Yeah. Mm-hmm.
Yes.
Yeah,
So we
correct.
have an automatic unpacking station for kind of the higher volume production customers that actually automate the removal of the parts from that powder and the recycling of that powder. And so it takes that manual step out.
That's perfect. All right. Okay, so we just completed everything. We went from, the how to do the pre-processed material loading, then we take it to the printer. Once we have printed the parts, we do the cooling down. There's two ways of doing that: natural cooling, fast cooling. And then when we have completed the cool down, we do the extraction of the part here manually, or as Wes was mentioning, we have an automatic unpacking station for big volume. And then once we unpack the parts, we're ready to clean them, bead blasting, air blasting. Those are the options. And for the last step, that is the optional one, that is the finishing. I'm going to pass it back to Wes. He's going to take you through the different steps, the different options that we have here. Wes?
Awesome. Thank you. I'm going to go ahead and share my screen again. All right. Pardon me. Okay. So a quick little recap of our workflow real quick before moving ahead. Again, we start with the file preparation and sending our job to the printer. We then have our materials mixed and loaded into our build unit. We take the build unit into the printer for printing. We remove that build unit and allow the parts to cool. We do that either in the natural cooling unit, in the build unit itself, or in the processing station with the fast cool. After that, we have unpacking that is done at the processing station manually, or for more high volume applications, can be done in our automatic unpacking station. And then the last step is a bead blasting process, which is going to remove any residual powder from the surface. And there was a question on this earlier: how robust are the parts as they're removed from the powder? And I'm going to extend that to during the bead blasting process as well. They are quite robust. So, definitely there are limitations with in terms of, your aspect ratios of how long and thin and kind of fragile your design is. But in general, we have very strong materials. These are engineering grade nylons mostly. So they're going to be able to hold up to that unpacking and bead blasting process. We do a quick little air blast after bead blasting to remove any sort of residual blast media from the surfaces. And then we have this secondary post process that can be done to enhance look and feel or performance of the parts. And that's what we're going to take a look at a little bit next. So this isn't going to be an exhaustive list of all the different post-processing options out there for MJF, but I wanted to show a few of some of the more common ones. So the first one out there is dyeing. And so here you have an example of a gray MJF part dyed black, and this is going to be a very inexpensive, easy way to achieve a nice uniform color on the surface of your parts. So here, this example, it's black dye. That is definitely the most common, but there are companies out there like Dye Mansion that are offering color dye solutions for our gray parts, and they can actually achieve some pretty interesting colors through that process. Painting is going to be another option to add color uniformity to your part. And you can see here the example at the very bottom. Depending on the amount of primer you apply, the amount of sanding you do, and polishing you do, you can achieve different levels of finish depending on that, up to a very smooth, high gloss Class A finish if required. So painting is going to be an excellent way to add color and to add things like UV protection, scratch resistance, the same type of things that it's going to improve on other types of manufactured products as well. Chemical polishing is, I would say, gaining traction, maybe the quickest of any of the smoothing type of post-processing technologies out there. This functions by introducing a chemical agent in a vapor form in a chamber to our parts. And this is going to smooth those parts out. And it's also going to make them glossier, shinier. It definitely seals everything in, makes everything more fluid tight and airtight. And it's going to improve the look and feel. So we're seeing a lot of success, a lot of traction with chemical polishing recently. Hydrographics is one of my favorite post processes just because of the different patterns that can be applied here. This works by depositing a thin film to the top surface of water, a big water vat. And then you dip your parts in and it's going to transfer the ink from that film to the surface of your parts. You're seeing a wood grain texture here, but there's literally, limitless possibilities for the different patterns you can apply with hydrographics. It's already very common in industries like automotive. It works well on MJF as a substrate. And then last but not least here, we have electroplating, which is interesting not just from a cosmetics standpoint, but also from a functionality standpoint. If you need to add conductivity to your parts, if you need really high strength to weight ratios, it could be interesting there. Electromagnetic interference shielding, a lot of interesting functionality improvements that come with electroplating. The example you see there on the bottom is an example of a nice mirror finish that can be achieved with MJF parts, but I will warn that definitely comes with some elbow grease and a lot of manual sanding time. So again, not an extensive list of all the different post processes out there for MJF, but a few kind of handpicked that I wanted to share with everyone today. All right, next up here, we have our materials portfolio. And we'll take a look at the different materials we're offering today on our Multi-Jet Fusion platform. So the first is our most common, I kind of call this our workhorse material. It's going to be our nylon PA12. And so this material is going to offer, in my opinion, the best balance between part cost, mechanical properties, dimensional accuracy, all of those things. So, in terms of mechanical properties, you're looking at a tensile strength of about 50 megapascals to give kind of reference there. A very strong, high grade engineering material, useful for a lot of different applications. The next material on here is our PA11, which is similar to our PA12, but it's going to have a little bit different properties. First of all, it's a renewable material. It's sourced from castor oil, so it is renewably sourced. But it's going to have increased ductility, allowing parts to be a little bit more tougher, impact resistant, and it's going to be useful for kind of more of those high impact types of applications that we're going to look at later. Then next we have a glass bead filled nylon, our PA12 glass beads. And this is going to, again, be similar to PA12, but it's going to have a little bit more stiffness. And so to give reference there, you're looking at a modulus of about 3,000 megapascals. And then our last rigid polymer we have available for multi-jet fusion is our high reusability polypropylene. This is a genuine polypropylene, which is helpful for several reasons. It's going to be very chemically resistant, have very low moisture absorption, and is going to be our lowest cost material in the portfolio. It's going to have great weldability, not just to other 3D printed parts, but to injection molded polypropylene parts as well, which is enabling a lot of new possibilities in the market. Definitely, a lot of potential here for this material, especially for industries like automotive, where polypropylene is very common. And then last on here, we have 3 different types of elastomeric materials available. We have the BASF TPU and our Lubrizol TPU. The BASF is going to be available on the 5200. The Lubrizol is going to be available on the 4200. And then we have a TPA, which is another type of elastomer that is also going to be available on the 4200. All right, so those were some post processes, our materials, and now we get to head into my favorite part of the session, which is our applications showcase. So Carolina is going to show here a few different part types. And I think one of the questions that was asked earlier was around, what are the most profitable or the highest success applications you're seeing right now with the technology? Well, that's what we're going to cover right here. So here you have a dental mold from Nivel Medical. And this is going to be, I would say, a very successful application space for MJF. You think of dental aligner industry, what you need are thousands and thousands of unique parts every day to supply this market. You could not do this without some sort of additive manufacturing technology. It would be very difficult to do without a high volume production type technology like multi-jet fusion. So common customer of ours that gets brought up, Smile Direct Club. Think of a farm of dozens and dozens and dozens of our printers producing tens of thousands of unique parts every day. Very interesting use case there, and where we are seeing a lot of success. Here is a very cool demo part of a pneumatic gripper design. That is something that would be very difficult, actually impossible to produce with traditional manufacturing, and very difficult to have function with other types of 3D printing technologies. This uses air pressure. It is pneumatic. And so it is a great showcase of how we are fluid tight in these parts here with our PA12 and with a lot of our other materials. Here we have a prosthetic from Glaze Prosthetics, and it is an excellent example of painting as a post-processing technique. I think this company has mastered post-processing of MJF. You can see the level of finish possible with the right amount of attention to detail here, like Glaze Prosthetics is showing. We're seeing a lot of success in the O&P orthotics and prosthetics space as well. All right, so here we actually have PA11. This was a design from Zigzag, and it is one of my favorite applications to showcase here. And so you think about the beginning of the COVID pandemic, there was a huge supply chain shortage of a lot of PPE and a lot of things for testing. And so HP stepped up, in partnership with a couple other companies to start producing these nasal swabs for COVID testing. And so these were produced with PA11. Carolina can show just how flexible they are. This is a very critical application where parts are getting, put definitely very far up patients' nostrils, and some type of breakage would be catastrophic in a scenario like that. So they needed a material that was robust enough that they could trust for this application during this time of crisis. HP was able to step in with our PA11 material and rise to the occasion. Here's another PA11 example, and this one has been dyed black, so it's a good example of that as a post-process. And this is a helmet to help reshape cranial deformities in infants from Invent Medical. So we have some really interesting design going on here that is like a flexible mesh, and the flexibility is given by the design itself rather than the material. And PA11 was chosen here definitely for its increased impact resistance and durability. Another PA11 design. This is on, I believe, the i8 Roadster, and this is something that goes inside the door in the window rail assembly. And so it's an example of a lightweighted sort of optimized design that would be impossible to produce with injection molding, very hard to CNC. 3D printing and MJF was going to be the right solution for this type of part. All right, so now we have our polypropylene material. This is from Xtol, and it's an example of a chemical bottle that has been welded. You can see that seam there. And it's a great example of welding with our polypropylene. So here in this case, you're seeing, 3D printed polypropylene welded to 3D printed polypropylene. But again, like I mentioned, we actually have the ability to weld the 3D printed PP to injection molded PP, which is interesting for a lot of applications moving forward because it is genuine polypropylene and they are chemically compatible. Here's another interesting use case of a prototype of a door defroster. And again, you think of the automotive industry, a large majority of their plastic parts are polypropylene. They want an analog to do their functional prototyping with. Our material is going to be able to serve as that analog in many cases. Great, so now on to our elastomeric materials. This is BASF TPU, and it is a really interesting lattice design that enables, a certain level of compression with this same one base material. And these have been vapor polished and coated. So you can see you can achieve a really nice finish with that post-processing. And we have really, good flexibility compression set with this material. Another lattice design example from BASF TPU, and this is from Superfeet. You have a lattice 3D printed midsole, and I'm very excited about this type of application. I think we're going to start seeing a lot of these 3D printed midsoles out there on the market. What's interesting here is, again, with that same one base material of TPU, you can vary the size of these unit cells, the shape of the unit cell, the beam thickness, and by varying just the design itself, you can have completely different properties of these midsoles. So imagine, in the future, based on how you run, what the pressure map of your foot looks like, you can have a custom-made 3D printed midsole that is specifically tailored to you. So that is, I think, what is coming in the future, and we're just right now seeing the tip of the iceberg. Here's a really good fixture application with TPU. This is kind of soft touch tooling to prevent any damage coming to parts. This is a company, Vestas, and this is something that will hold a wind turbine blade. So it is durable enough to stand up to the intense weight of that part, but it's going to have that flexibility and softness to prevent any sort of damage coming to that part on the assembly line. Great. And so this is an application from Kupol. Again, another sort of lattice type design. And this one is an example of the design being custom tailored towards impact resistance, right? Or absorption. And so this is going to be for a football helmet. And it's going to be, again, tailored and engineered to absorb as much of that impact force as possible during a collision. So now we have some TPA parts. Really good examples of vapor polishing on TPA. You can see this looks to me like an injection molded part. Very nice, high quality finish with that combined post process. This is just an example from a company, Go Proto, that they designed to help exemplify kind of the material properties of our TPA. Great flexibility, durability, and great finish with that vapor polishing post process again. All right, so as you can see there, a lot of different applications spanning a lot of different industries, whether it be automotive, medical, orthotics and prosthetics, industrial, jigs and fixtures. We really are touching on a lot of different applications out there. And, it's going to be the types of applications that are requiring high throughput, high quality of parts. And so it's very exciting. I think we are just, again, seeing the tip of the iceberg here in terms of our applications, but already a lot of very interesting things out there today. So now I'll hand it back over to Carolina to go into the customer panel.
Okay, thank you so much, Wes. All right, so let's jump into the last session, the last part of this webinar, that it's the customer panel. We have with us Kason here from iSolids. Hello, Kason. How are you? Good morning.
Hey, good morning, Carolina. Thanks for having me today.
Of course. All right. Do you want to introduce your business, your company, and introduce yourself, introduce the business as well? Yeah.
Sounds good. So I'm Kason Knight. Quick backstory: as a mechanical engineer working in the oil and gas industry for the majority of my early career, and got into 3D printing basically during a downturn in the industry. And we were looking at new ways to keep some of our research and development projects going, and saw the way that 3D printing was evolving very quickly. And so that was something I turned to in order to keep some of our engineering projects going when I was continuing to work there. And that kind of leads into the story of how we got created at iSolids. Basically, we were doing engineering projects and we're utilizing 3D printers, as many were, for creating prototypes, and quickly saw that the speed and the production capabilities that the printers and the cost effectiveness were opening a new market for evolving 3D printing just from prototyping into production manufacturing. And so we kind of jumped on that and we said, hey, we still offer and do engineering services as well. But I think our core business as a company is definitely around production manufacturing. And the way we always describe it is we're a manufacturing company. We just happen to use 3D printers as our tool of choice.
That sounds good. All right. I know you have some applications that you would like to show us, Kason. Let me just show the first one. And this one is impressive. There's a video too. So if you want to walk people through this one.
So this one's interesting. There's a little bit of a slow-mo video going on there. So I think this is very intriguing just because as a mechanical engineer, I look at this device that came out, I think it was in the 40s or late 30s. So it's been out for almost 100 years now. And to see the mechanics involved in this, it's essentially a mechanical digital switch, the way it works. So it's just really fascinating. I can kind of geek out a little bit about it, but what's interesting about this is we have a customer who is very commonly will repair these or restore these and then resell them. And you can see there in that middle picture of a gear on the left that has a crack down the center of it. That's the original gear, and it's printed, or not printed, but it was produced in nylon. Over time, it ages and it cracks. And that gear is basically the drive gear for the entire main shaft on the typewriter. And so it has to be perfectly balanced and very geometrically accurate, because that literally drives a gear shaft, which everything else runs off of. So if there's any imbalance, then that perfect timing that is required for those keystrokes to basically turn everything at just the right size. So, I mean, I could probably talk about this for a long time, but it's very intriguing the way this technology was developed back then and everything else. So this next one is actually a customer that we've worked with for a very long time. And we started off working with them before we even acquired MJF. And we were producing brackets out of FDM using ABS material. And then we were acetone vapor washing them to increase the strength. But once we acquired the MJF technology, we showed them what they could do. And as often is the case, our print farm is very recognizable to many people in 3D printing. But once we show them what MJF can do, they become very quick believers and adopt the technology and the application. So this is another example of that. This particular customer is named Hylio. They develop and create software for agricultural drones. Okay. And so a lot of the components that we create for them, or not create, they design it and we produce it for them, are going on very heavy duty. As you can see, these are no DJI consumer drone. These are big, heavy drones, and they hold a lot of weight, get exposed to a lot of different elements. MJF holds up well, and the customer is definitely pleased with the results there. And the last one is Photosound Technologies. This is, again, another customer that we started off with FDM, transitioned over to MJF. This was a component that was also being contemplated to be CNC'd out of aluminum. But for cost and production speed, we switched them over to MJF, and they've been very pleased with the results. And I can maybe touch on this in a little bit as well, but one thing that's note about this application is it was specifically designed for CNC, and with very minimal design changes, we were able to optimize it for MJF.
All right, perfect. So I have some questions for you, Kason, and I'm also going to invite the audience if they want to ask Kason any questions, please just type it here in the Q&As and we'll definitely fill that. All right, so the first question that I have is around the advantages to your customers in producing parts using multi-jet fusion. I know you use other technologies, so can you elaborate a little bit on the advantages that you find?
Absolutely. So the first one is normally part quality. Many of our customers, especially on the when we're doing full-scale manufacturing, FDM can normally produce a result. We do worry about the isotropic or non-isotropic strength of the part, but mainly they don't want the part to look 3D printed. Most people have a perception that a 3D printed part is not of the same quality and strength. In an FDM, that's often the case. And so what's great about MJF is it doesn't look 3D printed. The layer visibility is there with the correct orientation and optimization is essentially invisible layers, especially after certain post-processing. It looks injection molded in many cases. Of course, the second requirement is normally the strength. With end-use functional parts, you have to have the strength required normally be synonymous to injection molding. In our testing, we found it to be anywhere between 95 to 98% the strength of an injection molded part, again, with proper post-processing and calibration of the machine. So from cosmetic and a strength standpoint, it's a great way to bridge the gap between prototyping and full-scale manufacturing. And in many certain circumstances, it's suitable to produce at full scale. And customers never have to go to injection molding, which allows them for design flexibility. They can make iterative design changes without having that initial tooling cost to come back around every single time, which in turn allows them to stay ahead of the market as well. But the last and most important reason that we like MJF, and in turn many of our customers do as well, is the production speeds and the cost per part. When you're manufacturing at scale, you have to be able to manufacture fast. You have to be able to meet those demands. And like anything, if you scale up, then you can normally decrease your cost and become very economical.
Okay. What you actually covered my second question, that was the cost drivers, but that's perfect. I know that you currently have two of the 4210, so the 42 series, and then one of the 5200 series. And then you have a 580 as well. That was the prototyping machine that we used to have. But when it comes to production, what difference do you see in between the 4200 series and the 5200 series?
Yeah, so we of course started with the 42, I think right at or right before the 5200 was becoming available. Mm-hmm. And so when we went from the 580 to the 42, we went from a prototyping machine to a production machine. It was already a very nice transition, and we were very pleased with the results. The 4200 has been extremely reliable. From a production standpoint, when you're looking at manufacturing, you have to have uptime, and the 4200 was up 95 to 98% of the time, and our part quality rate was about 97 to 98%. So we couldn't ask for any more out of the machine, especially in comparison to FDM and SLA, which is normally, in our experience, around 85 at most percent success. And so from that standpoint, we're very pleased with the 4200 to begin with. I can say that we are personally even more impressed with the 5200. And the main reason is the production speeds. As anticipated, it's a rather than basically two passes across the print head or the print area, it goes to a single pass. So that reduces your print time from around a 17 to 18 hour cycle on the 4200 series to around 11 to 12 hour cycle with annealing and cooling time, at least in our workflow. So that extra 6 hours is critical because that allows us to go from essentially 1 to 1.5 builds per day to 2 full builds per day. So in our workflow, the 5200 outproduces the 4200 by about 1.5% or 150%. So it works really, really well in that environment. There's a lot of other benefits to the 5200 series. And what I believe is HP did a really good job of making incremental improvements to what was already working, which is all we could really ask for without sounding, I guess, cheesy in saying that. But for example, the cooling units, the build units were often, because the most wear and tear, there's a lot of mechanical movement as that build plate goes up and down in the Z-axis. So in our experience, that was the most common failure point. And so with the 5200, adding the cooling units, that added extra redundancy. If one of our build units did go down for maintenance, we had the cooling unit available, so we can basically keep our same workflow by not having to tie up an additional build unit with the fast cooling process. So those are all intricate details that as you work and really try to squeeze out every bit of what these machines can do, but it definitely makes a difference. That doesn't mean that the 42s don't definitely have some benefits as well, especially for our case, we use them for the TPA material, which does really well.
Perfect. And that leads me to the second question that I have for you. It's around materials. I know you're using PA12 and you're using TPA as well. Why did you decide for these specific materials? Can you elaborate on that?
So as mentioned, the PA12 is kind of the gold standard. It has an amazing mechanical balance, cost, speed, everything. It kind of checks all the boxes, and it's most commonly known as well. People think about nylon, they think PA12. So from a service bureau or contract manufacturing perspective, that's definitely our most common material because it works across the board. Mm-hmm. I would say the reason that we selected TPA is our I guess, flexible material of choice out of the three that we were evaluating, which was the BASF TPU, the Lubrizol TPU, and the TPA material. They were all had very great results. What drew us to TPA specifically is it's slightly softer than the TPUs. I think the TPUs are around 95A hardness, whereas the TPA is around 90A hardness. In most flexible applications, we want the softest, most flexible material that we can get. One of the other things that we have to consider is the workflow. Again, being optimized for production speed and quality, the workflow associated with the TPA material was very synonymous to the workflow associated with the PA12. So we didn't have to do anything that was outside of our norm as we switched between those two materials.
Wow. Okay. Perfect. So let's let's talk about the workflow, because it's just mentioning, the different workflows that you have with each one. What was your experience? What's your experience designing for Multijet? And did you have to adapt the processes that you already had to work with our technology?
So when we normally get the question about designing for Multijet, I normally respond with, it's not required, but desired. That sounds a little cliche, but it's true. In many circumstances, we can take a part and we can print it in MJF. But the two questions are, is it going to be the most cost effective? And are we going to get the most repeatability and reliability out of it? A prime example is going back to the Photosound Technologies. They designed it for aluminum to be CNC. So there were some parts that were big and bulky. And generally speaking, in CNC, the less material you have to remove, the lower the cost. So it's kind of the opposite in this circumstance. We want to reduce the amount of material usage, in turn, reduce the amount of agent usage, which ultimately results in a lower per part cost. So we were able to produce it and prototype it directly as the design was. That allowed them to not spend any upfront engineering time to basically test the technology, see if it would work for their application. But then once they were satisfied with the results, very minor amounts of changes, basically to reduce volumes, add lattice structures, allow them to optimize that. So, but ultimately as a company, we fall into three different categories. As a contract manufacturer, where we don't have any control over the design. As a design service, where we design without limitations to even our own abilities, as well as a design for manufacturing, where we're intending to manufacture. And again, I would say the Multijet does well in all three of those categories, where we can produce the parts. But with just a little bit of extra effort or a little bit of optimization, we can just get the cost down a lot. And that's normally the driver.
Perfect. All right, with top of the hour, Kaysen, I don't know if you have anything to add. If you want to let the people know if they want to contact you, how to do that. I'm sure they can go to your website, correct?
Yeah, absolutely. I appreciate that. Our website is i-solids.com. And from there, there's an instant quoting feature. And we offer, of course, Multijet Fusion, as well as advanced post-processing. That was touched on by Wes. And I couldn't agree more that a lot of advanced post-processing really makes these parts pop. Vapor smoothing in particular is a really great one for water impermeability. That's another reason that we chose TPA. I think GoProto did a great job showing what Vapor Smooth TPA can do. So yeah, definitely you can go to our website, i-solids.com. We're also definitely on LinkedIn and all the other social medias like Facebook and Instagram. You should be able to search for iSolids. And I'd love to connect with anybody on the webinar on LinkedIn as well. You can just search for my name and it normally pops up because it's unique enough.
All right. Thank you so much for your time. I appreciate it and sharing with us all your experience and your knowledge, Kason. Thank you.
My pleasure. Thank you.
All right. And so we're going to move now into the last 3 minutes that we have right here. 2 minutes. Wes, I don't know if you have any other questions that we can just take now, right now.
Yeah, we have a few. So one of them was about our nasal swab application that we talked about earlier. The question was, were the nasal swabs and container all printed together and assembled? So, if you remember looking at those nasal swabs, there was kind of like a box and all the nasal swabs were inside of that box. And so what that box was, it was actually a sacrificial cage that was going to help us retrieve the parts during the unpacking process. If you can imagine all those tiny little sticks floating around a build, it would be pretty challenging to retrieve all of those and clean them all if they were all kind of floating around in space. So we printed these sacrificial cages to keep them together during the unpacking process and actually to help during shipping as well. So that's what we did there. We see it with a lot of applications where we have smaller parts printing sacrificial cages to keep everything together. Another question, and if Kason is still there, this might actually be interesting. He already brought up one example, but the question was, is it possible to replace aluminum material with this material? So Kason already talked about one application. Kason, have you seen any other instances where aluminum parts have been replaced with MJF?
Definitely. I saw that question come through and I was hoping I could touch on that. Absolutely. We see that a lot. And we normally, when we get those requests, it's people asking us for metal 3D printing, which is definitely something that we can help with as well. But most often, it's normally just not the economics of it. When you can 3D print in metal, you can normally CNC it depending on the part, unless it's really complex aerospace, and that could be a whole topic in and of itself. But absolutely, it's very common for us to take an aluminum part and basically print it as is and get very good results. But it just goes back to making those optimizations for cost. And so it's definitely doable. We see it all the time. And the only thing I would recommend in many cases is aluminum is often desired for its environmental resistance. And so vapor smoothing is, again, something that we would recommend for something like that to make sure that there is no water or gas impermeability. So
great. Yeah, like Kason was saying, we see a lot of applications that, were traditionally CNC'd out of aluminum. I think particularly of a lot of jigs and fixtures, especially that application space. A lot of times we can achieve, the right properties with our material. We can do, a lot of light weightings, definitely a lower cost. So yeah, there's a lot of applications where it makes sense. And then there's one more here, Carolina.
One more.
Okay. It's kind of a tricky one. And again, Kason, I would appreciate your insight here. And it's kind of, what is the most frequent, challenges or technical difficulties with the technology?
I would say for me, it's just understanding the slight variances. We get it a lot where people are familiar with FDM, and it sounds maybe self-inducive, but a lot of times they will limit themselves in the design for FDM, and we have to kind of break that mindset. So it's not necessarily a technical difficulty with the machine, but it's more of a just changing and breaking those molds. They are machines. There are times that the machines will have actual technical difficulties. I will say that HP does a pretty good job of responding, at least in our experience, is far superior than the other services that we work for. And that's not intended to be a promotion of sorts, but I'm just being transparent and truthful in that. So I would say the most common technical difficulty is normally associated in our experience with the build unit. But the great part about the system and the fact that it is modular is if you have to have one build unit that's normally down, you have other build units to continue production. So it's a system that's very well set up to allow redundancy.
Perfect. Very well put. I appreciate that, Case. And like you was saying, I think one of the biggest challenges I encounter too in my conversations is kind of this mindset shift. You know, a lot of people have traditional manufacturing in mind, and getting them to think multi-jet fusion or think additive manufacturing in general can be a challenge, but is definitely, you know, something that we are seeing gradually shift in the market. So yeah,
All
that's it
right.
for that, Carolina.
Yeah, I think we got, we're a little bit over time. I just want to appreciate everyone's time. I saw that there was a question if this presentation is going to be shared. I can tell you guys you're going to get a follow-up email with the replay of this webinar. So if you want to watch it again, you totally can do that. If you want to continue the conversation with the 3D printing specialist, you can also do that. So stay tuned and watch out for that email that you will be getting soon. And with this, I want to thank everyone to join this webinar. I really appreciate, I appreciate Wes time and also Kason. And I hope everyone to have a good day and happy holidays. Thank you so much for joining.